Go ahead. Thanks.
So thanks for the opportunity. So basically, I'll be talking about a class of submodular functions for document summarization. So I'll define all these terms, but the basic point is that the paper aims to give a formal sort of setup for document summarization problems, and basically provides the necessary formal elements. So let me begin by actually defining the various types of summarization and the problem itself. So summarization basically is that you have a document and basically you want some sort of summary for it, some sort of second document that is shorter than the first one, which summarizes the key points and concepts. So that is basically summarization. Now there are sort of few types of summarizations that are mentioned in literature. The first one is extractive summarization. So it basically selects words and phrases from the original text, which are most representative of the document. And, for instance, some sort of key phrases that it can select. And basically, the key point is that it doesn't rephrase the information that is there in the document. So it basically selects, elements from the document in order to represent what is going on in the content. In that process, it basically ends up cutting the the repetitive sort of mention of some concepts and basically makes the whole thing more concise. So extractive summarization itself can be divided into two subtypes. One is query based and the other is generic. So generic is basically something like come up with the key phrases for the documents, and query based is you basically have some sort of query. So let's say you have a document about Paris and London, and you basically want to only sort of look at summarize the content about Paris. So that is query based. So you'll have a query saying that I just want the information for Paris, and it will basically generate a summary from the document only giving the elements about Paris. The other sort of summary, which we are more commonly aware of, is abstractive summarization, which is a summary that is basically rephrases the original sort of information and doesn't just use the subsets of words or language elements from the original documents, but basically rephrases it and produces something that is concise. So this is the sort of summarization that is done by LLMs, etc. So and then of course there is hybrid sort of approaches, which is that you can generate the keywords of extractive summarization and then basically feed it into an LLM to produce a rephrase summary.
Mm-hmm.
So these are the various sort of summarizations that are mentioned in literature. Now I'll basically come to
Harshant, can I ask you just a follow-up question because you're starting very general. Now, in addition to summarization, can like LLM be used also for extension, right? So maybe you actually don't want it to be shorter, but want to like fill in the blanks. Have people thought about doing this, or like
yes,
sometimes like you have a discussion, but it has a context, and then you actually need to sprinkle in new terms. Explain things in more details. I wouldn't call it summarization, but some like processing. Have people been doing that?
So that has that has been looked at. Of course, you can basically elaborate on the content that is already there,
Mm-hmm.
but I haven't seen an objective function sort of
Right. That's what I
approach
mean.
towards
Is there
it.
a theory behind it? Kind of
So
objective function.
so basically, as far as abstractive summarization and elaboration is concerned,
Mm-hmm.
there is no objective function that you can write which does this. So this objective function methodology that I've seen for only works for extractive summarization.
Mm-hmm.
For extractive summarization, for abstractive summarization, it basically is some sort of sequence prediction, and
Mm-hmm.
the summary that appears is some sort of emergent phenomena from those objective functions. So there's no direct summarization, there's no direct objective function that you maximize or minimize in order to get an abstract summary.
Okay,
it just emerges from the objective function that you're using for the sequence prediction that is there. So basically, most of the extractive summary algorithms can be cast as, so basically a lot of things that people were doing while generating extractive summaries, basically they can be cast as maximizing an objective function that is submodular. I'll come to what submodular means, but submodularity persists despite. So basically, it is a general, basically provides an opportunities for some formalism, because there can be many similarity measures and coverage functions, but submodularity persists because most of these functions that you write can be shown to be submodular. I'll just come to this. I'll basically describe why this is useful and stuff.
Mm-hmm.
So now one of the advantages of submodularity is that there are theorems for greedy algorithms that basically guarantee an optimal solution in a fixed time. So basically, if you're able to prove that the objective function that you're maximizing is a submodular function, then a lot of machinery that is already available, as far as operations research and work on some modular functions is concerned, that you can use to prove that ultimately, there are optimal solutions that you can arrive at in a fixed time. So what are submodular functions? So basically, submodular functions are defined on sets. So basically, f is a set function. So basically, you have some sort of sets f, a, and b, and you have a function that sort of takes you from a to the real numbers, takes you from a set to real numbers, and basically, a submodular function is such that if you add elements to the set A and if you add elements to the set B, the increment in the function that you have, the incremental value decreases as you go from A to B, and A is a subset of B. So that is basically a submodular function. It's a set function that basically has this property of diminishing returns, which is what is essential. That basically, if you add a set of elements to A and if you add a set of elements to B, and B is greater than A, then the incremental value of the function will decrease with a larger set.
Does it work for like entropy, entanglement entropy, or something like that?
Yes. So entropy is exactly a submodular function. So that is mentioned in the paper also, that it is a submodular functions. So there are other mathematically equivalent definitions, but the main thing intuitively to sort of remember is that it satisfies this property of diminishing returns. That if you add an element to a larger set, the incremental return is less.
Mm-hmm.
So submodular functions have their roots in game theory, operations research, and combinatorial optimization. And they are basically closed under this weighted average operation. So if you have a bunch of submodular functions and you create a weighted average where the weights are non-negative, then that will also lead to a submodular function. So this is an important property of submodular functions that is mentioned, that if you compose it with a concave function, then it basically a non-decreasing concave function, then it remains non-decreasing submodular. So basically, a lot of these results that are there require monotonicity in addition to submodularity. So those are called like monotone submodular functions. So that is the class of functions for which a lot of these theorems that I'll be showing you. So now, the setup of optimization problem is that you have some sort of, why is this relevant to the sort of problems that we have in summarization? So basically, you can have the set of, we represent the set of all sentences or other linguistic units. So, basically the kind of linguistic units that are mentioned are words and bigrams and n-grams. So you can either deal with sentences or basically more fine-grained linguistic units. And basically, the task of extractive document summarization is to select a subset S to represent the entirety of the set. So basically the set of, so V is the set of all sentences that you have in a document, and you have to select a subset of that big set that basically, optimizes a particular function. So an objective function that is there. So that is the task of extractive sort of summarization. That the sort of function that we'll be describing is some sort of coverage function. So how much of, how much the subset covers the bigger set in some intuitive form. So I'll come to actual functions that do this, but this is what it is. Basically looking at similarity of the smaller set to the bigger set. So how well does it represent the bigger set? So those are the sort of functions that we look at. So if you use some sort of set function f, which takes from the set of subsets to R to measure the quality of the summary, then you can basically have this set up for. So basically, the summary that is optimal is one that maximizes this fs subject to some sort of constraint. So these constraints can be like something like the number of characters should be like fixed. So these are the sort of constraints that are there. So this is a typical like combinatorial optimization problem that is there. So that is how you basically set up the optimization problem, which is relative to summary extraction. So now basically, this is an NP hard problem, the problem that has been set up right now. And basically you can show that if, the function f is submodular, then basically a lot of, theorems work. And basically you can show that there's a practical greedy algorithm, which basically solves the optimization problem fast. So in all these cases, basically submodularity and monotonicity are needed. And, so basically what is shown is that most of the commonly used functions are submodular, but not monotone. So what the aim of the paper is to design functions that are both submodular and monotone, which can be basically optimized when generating summaries. So now one of the commonly used measure is this maximum marginal relevance. So basically, as I said, it is some sort of similarity measure. So this is for a query-based summary, which is there. So you have a query and you have some sort of element that you take from the text which is there in order to see whether it should be included in the summary or not. And basically the objective function gain. So this is not the objective function. This is the sort of step that you take. Let's say in gradient descent, you take a step. So the increment in that step is basically some sort of lambda, similarity in SKQ, and with a linear combination of some sort of similarity in SI to SK. So what this basically says is that, SK is a sentence that you want to include or not, and Q is the query. So basically it rewards the similarity of the sentence with the query, and basically penalizes the similarity between two sentences. So if two sentences are too similar to each other, they should not be included. And if a sentence is basically similar to a query, then it should be included. So these similarity measures can be anything. They can be cosine similarity or anything else. And basically what he shows is that if you have a function that basically has these increments, then it is submodular. So this is basically the step that you take, the sort of change in objective function. So he designed an objective function for which this is the change in the step. This is the change in the objective function when you take a step. So step is basically, basically trying to include SK or not. So you basically, have some word or some other linguistic element from the document that you want to include in the summary or not.
So, but that involves like breaking everything into the sentences, right? So this only.
Yes.
So you first have to break into the sentences. Okay.
So the breaking into sentences, so you can also break into words. So that basically, there are many approaches used. Basically,
no, but the point is that the meaning of the words depends on the context of the sentence, and so whether it is similar or not similar to the query, it depends of where this appears, and so it becomes.
Yes, that's a good point. Yes, so basically one should deal with sentences rather than individual words. Yeah, but the formalism works either way, but like I think that's a good call. Basically, sentences.
No, but I mean it's asking for some kind of attention mechanism in quotation marks, meaning that depending of where the word or sentence or some text appears, it may have different meaning, and so the maybe has to be a separate neural network that is trained to do that. Okay, I don't know. Okay.
Yes. So basically, it shows that an objective function that has this sort of form for the step it takes is basically submodular. So, but it's not monotone. So you can, this is, I can basically go through this and tell you. So basically what happens is you have this term, which is the similarity in Si and Sk, and I is basically an element of S. So S is basically the set of sentences that is there. So I is an element of S. And basically, if there is a bigger set that is there, which I is an element of, then, the similarity, this term would be less than equal to this term. So basically, the reason being that, this already includes these terms. So basically, additional terms that are arising from I being a set, I being an element of R, leads to maybe a possible of a higher maximum, being there. So this is greater than this, and basically because there is a negative coefficient here, so basically the signs flip, and basically it satisfies this diminishing returns property. That if you add to a bigger set, then the return you get is smaller than if you add to a smaller set. So basically, so this is basically submodular, but it's not monotone. So basically, the greedy algorithm constant, so that the guarantee that we had that we'll find an optimal solution in some fixed time is not there. So now basically we look at monotone submodular objectives. So basically what he tries to do is design objective functions that are both monotone and submodular, so that the arsenal of theorems that we have which work for this set of functions work for this. So basically you have some sort of f of s, where s is the set of basically s is the summary, and you're basically evaluating the summaries. So f of s is basically some sort of L of s plus lambda R of s. So LS measures the sort of coverage of the summary in some sort of way. So that's how he breaks it up, that it measures this the coverage of the summary and some sort of similarity between the summary and the document itself, the whole document. So that is the sort of thing that L measures. And R is some sort of, rather than penalizing redundancy, which led to the previous objective function being non-monotone, you basically reward some sort of diversity. So that diversity is defined later on. I'll just get to it. Basically, what you do is cluster the words in the original document, and then basically you sort of into basically distinct classes. You basically cluster the sentences, not the words. You basically cluster the sentences into distinct classes, and then you would want, only one sort of element from each class. So that is diversity. So rather than repeating, information that is already there, you would want one from each class. So this clustering
Hold
is
on,
itself.
isn't the first term doesn't it do the same? I mean, basically, if you want to have most information from the document in the summary, it is
Yes.
not. It is to your advantage to have this information to be diverse, or otherwise you won't be able to get as much information from the document. So isn't the first term already has it, or I'm missing something?
So the first term is basically the similarity of the summary and the document, which is basically that the summary represents. So fidelity is what the paper refers to. That it basically gives you a faithful sort of representation of the whole document, and R is some sort of measure that basically rewards diversity, which is that there is an algorithm they use to break the sentences into clusters, and then you would want only one element from each cluster rather than having a lot of them. So that's basically what it is. So it is basically decomposing the problem into fidelity and basically diversity. So you would want a diverse set of sentences which basically convey the information faithfully. So this is the typical format of some sort of objective function with a regularizing term. So as I mentioned, Shannon entropy is also monotone submodular. Now the actual function of the actual, how this L of S is actually implemented is through these functions, which are, like sum of I over. So V is basically the set of sentences in the document. And basically you have some sort of, cosine similarity distance, which is there, which can be cosine similarity or something else. And so it doesn't matter what sort of similarity measure you use, the function would still be submodular. So this sort of form is taken because it gives better results. But basically, when alpha is equal to 1, it reduces to similarity measure. So it's something similar to some sort of average similarity of the summary to the document.
Mm-hmm.
So R is again the P of I is some sort of clusters that you break it into, and then you basically have a function R, which basically rewards this selecting sort of from clusters very economically rather than basically repeating stuff that is there. So basically R rewards that. And the actual functions used are these. Basically, you have some sort. So Wij is the cosine similarity, and basically, R1 of S is basically this sort of function which is again submodular. So it is basically designed to be submodular and rewards diversity. So yeah, this is basically the form of Wij. So basically, this is cosine similarity. And thanks for your attention.
Thank you, Harshant. Any questions? Well, I still have a question. I don't think I completely understood that formula. So maybe can you go back and...
Yes, sure.
I
Which
also have a question.
Oh, and Preeti, okay,
Yes.
Preeti, go ahead. Ladies first.
Okay, can you go one slide before previous one?
Yes. Yes.
Yeah, I'm having confusion with equation 2.
Okay.
Yeah, that was
Okay,
my question too. Go
okay.
ahead. Yeah.
Okay, so if I understood correctly, the
Yes.
first term, that ls,
Yes.
does that mean that, for example, you have your full document and
Yes.
then you summarized into something small?
Yes.
Okay, so how much that summary is, I don't understand what is the meaning of how much that summary is similar to your original document? I mean, how
So
are you? Yeah.
So basically, there is some similarity measure which is there. So there are similarity measures in basically NLP which are there in natural language processing which are used. So basically, that is how you measure how similar the terms in summary are to the whole document.
Maybe like something like mutual information is higher.
Yeah.
So once you have one, one, you know the other more. So some kind of the probability space. Yeah.
Is this
So you
equation
can
something like a Lagrange multiplier? So your lambda, I mean, let's say lambda is
It
0.
is. It is. It is. Yeah.
Yeah, it is something like that. It's basically
Yeah.
some sort of regularizing term, and
So
it is, yeah.
lambda is 0. What does that imply? When that means your
No, so
sum is perfectly. Yeah. Sorry. Yeah.
I
no,
think
no.
a
So
higher
lambda
lambda
is
is going to make it more diverse. It's like a trade-off.
yes, exactly. Yes. So lambda is something that is set by us. So so if it is 0, it means that the function that you're maximizing is just L of S, which is
Yes.
just this cosine similarity. So basically what you're doing is you're basically trying to, if you have a constraint on length, for instance, then you're basically trying to select the words such that they are most similar to the word in the documents. So that is what you do.
Yeah, that's a good example. So like you have a document and then you make sure that all of the capitals of all cities that appear in document appear in the summary. So that
Yes.
it's like at least one way of thinking about this. Something that is present there. It may not be the right thing to preserve, but then you preserve it. But then the other one, you're saying, well, I just also want it to be diverse. We want to have different cities, like if like Paris is mentioned 100 times and London once, in the summary I will just have one London and one Paris, something like that. I mean, I don't think I have a complete understanding of it that there is, but there's certainly a balance between the two. Yet in this bigger probability space that of course needs to be defined somehow. Yeah.
Yes. So that is a good way to look at it, that you have a document which has information about all capitals of the world, and then you basically want something from each capital, but you also want the whole thing to be similar to.
Right.
So that's the one way to look at it. And the way that you actually calculate this L of S and R of S is basically through these similar, cosine similarity, etc. So, these are the standard set of functions which are there to calculate.
Good. Thank you. Other questions? Well, my comment was only maybe if you correctly defined information coverage in LS, how much is information preserved in your summary, then maybe you will guarantee to have diversity because in order to have more information, it has to be diverse. I mean, I cannot really point my finger because I need to write some math equations here, but
I think one can say that this LS plus lambda RS might be some sort of, you might be able to rewrite it as some sort of entropy function.
Good. Yeah, exactly. So maybe it's more of a phenomenological guess rather than the final answer.
Yes, final answer. But
okay, that makes sense.
So these two terms can be clubbed into one if you have some sort of, yes.
Okay, very good. Any other questions, comments? Well, thank you, Harshant.
Okay, thank you.